In this video, let us see about the three-phase induction motor, its construction, working principle, the different types of induction motor, slip ring and squirrel cage motor, different power stages involved in the motor and the losses that occur in the motor. Then we will see about the advantages, disadvantages as well as applications of the motor. What is a motor? A motor is a machine that converts electrical energy into mechanical energy. So what is an AC motor? AC motor works with AC input and it will give you mechanical output. This AC input can be single phase or three phase depending upon the motor we use. Let us see the different types of AC motor. There are two types, asynchronous machine and synchronous machine. Synchronous machine will always run at synchronous speed. Asynchronous machine, induction motor comes under asynchronous machine. Here the motor will run at a speed other than the synchronous speed. So induction motor, there are two types, three-phase induction motor and single-phase induction motor. In synchronous machine we have alternator and synchronous motor. So in this video we will be seeing only about three-phase induction motor. So three-phase induction motors are widely preferred in most of the industrial applications. So depending upon the type of rotor they have, it is basically classified into slip ring induction motor and squirrel cage induction motor. Now let us see the construction of the three-phase induction motor. Basically any machine consists of two parts, stator as well as rotor. Stator is the stationary part and rotor is the rotating part. So in this induction motor we have outside stator which is stationary and three-phase supply is given to the stator, and rotor is the center part. You can see small circles which represents rotor conductors which is rotating. So this is stator and this is the rotor. In between and stator and rotor you have air gap which is represented by this yellow color here. So there is a air gap between the stator and rotor which plays a major role in induction motor. Let us see the stator first. So it consists of three windings. So each winding is 120 degree placed apart. So they are fed from a three-phase supply. When this three-phase winding is fed from a three-phase supply, it will produce a rotating magnetic field. There are two types of rotor. One is the squirrel cage rotor. It resembles the cage of a squirrel. And the other one is slip ring rotor, which is also called phase wound rotor or wound rotor. So here you have slip rings. Three slip rings will be there which are connected to the brushes. Next we have squirrel cage rotor. So this resembles the cage of a squirrel. So you can see the cage of a squirrel and the rotor also looks like that. 90% of the induction motors which are in use are of squirrel cage type because they have a simple and most rugged construction. If you see the construction of squirrel cage rotor, they consist of a laminated core with slots for carrying the rotor conductors. So here we don't have any winding, instead they are like heavy bars which are made up of copper, aluminium or alloy, and the ends of the bars are connected to two metal rings, or we can say they are shorted to the two end rings. Since they are permanently shorted, we cannot add any external resistance. If you are not able to add any external resistance, it means that we cannot change the starting torque of the squirrel cage rotor. If you see this picture clearly, the rotor is slightly skewed. So this is done to avoid magnetic locking and humming sound. What is that magnetic locking? Even though you give the supply, the motor may not be able to rotate because of the interaction between the stator and rotor flux. They get coupled together and the rotor will not be able to rotate. Instead it tends to vibrate. So that condition is called magnetic locking, and because of that you will get some humming noise which can be avoided if you skew it. Next we will see about slip ring rotor, which consists of three-phase winding, and one end of the winding is connected in star connection, the other end is brought out and connected to three slip rings. Over the slip rings we have brushes to connect to the external rheostat. So here you can change the resistant value or you can add some external resistance. In slip ring induction motor, we can easily add the external resistance, thereby we can increase the starting torque. If you see the squirrel cage motor, the starting torque is very less compared to the slip ring induction motor. So here in squirrel cage we cannot change the starting torque, but in slip ring there is a provision to change the resistance connected to the circuit and thereby change the starting torque. Rotating magnetic field is an important topic in three-phase induction motor, because without this rotating magnetic field, induction motor will not work. When you give this three-phase supply to the three-phase winding of the stator, three fluxes will be produced which are displaced by 120 degree. The resultant of this flux will interact with the rotor conductors or rotor current, and that produces a torque which makes the motor to rotate. So it is necessary to understand how this rotating magnetic field is produced in three-phase induction motor. Now we have to find at every instant what is the resultant flux. So for that, let us draw the phasor diagram. Phi r, phi y and phi b each is displaced by 120 degree. So this is minus phi r, which will be 180 degree or out of phase of phi r. So phi y, minus phi y will be here and minus phi b here. At 0 degree, let us find what is these values phi r, phi y and phi b. So phi r is equal to 0 because omega t is 0, and phi y equal to, we are getting minus root 3 by 2 phi m, and phi b is equal to plus root 3 by 2 phi m. We can see that one of the flux is 0 while the other two have same magnitude but opposite polarity. Now from the phasor diagram we will find what is the resultant flux. So we have phi r equal to 0, so let the phi r be 0, so leave it. We have phi y and phi b, magnitude is same, root 3 by 2 and root 3 by 2. Phi y we have to take minus sign also. So let me take this minus phi y and phi b alone, and its magnitude, it is root 3 by 2 phi m. Now let us find the resultant of these two vectors. So draw a parallel line here and draw another parallel line. Find the resultant value phi resultant. So here we have two vectors of same magnitude. So when two vectors are of equal magnitude, and if their angle is here, the angle between them is 60 degree, then resultant is given by 2p cos theta by 2. So in this case theta by 2 is 30 degree. Okay. So we will find resultant flux is equal to 2 into what is p, magnitude of this is root 3 by 2 phi m into cos into what is theta by 2? This is 30 degree. So cos 30. So if you simplify this, you are getting 1.5 times phi m. So the resultant flux is at omega t equal to 0 degree, it is equal to 1.5 phi m. So you note down this value. We are going to find the resultant value for different angles. Now we will find the resultant flux for different angles. Let me take 60 degree first and find the flux values. You can see that phi r is equal to root 3 by 2 phi m, phi y is equal to minus root 3 by 2 phi m, and phi b equal to 0. Again 1 is 0 and 2 have same magnitude with opposite polarity. So if you find the resultant, you will again get 1.5 phi m. Again you find for some other angle, take 120 degree or 150 degree, any value. I have taken 180 degree and finding the values. Again here this is equal to 0 and these two have equal and opposite polarity. Now you find the resultant, it is again 1.5 m phi m. So we can conclude that the resultant flux has a constant magnitude of 1.5 into phi m, but this will be rotating at synchronous speed in the air gap between the stator and rotor. Okay, we will see about synchronous speed later, but you see, though you are giving 3-phase AC supply, the resultant flux is a constant magnitude, has a constant magnitude of 1.5 times the flux. Let us see the principle of operation of 3-phase induction motor. We can see that the stator is green in color and given a 3-phase supply. The rotor, now initially it is stationary. So here it is represented by pink color is rotor. In between we have air gap. So when 3-phase supply is given to the stator, it will produce a rotating magnetic field. We have seen that it has a constant magnitude of 1.5 phi m. So this field is rotating at synchronous speed, which is given by 120 f by p, where f is the supply frequency and p is the number of poles. So if I give a 50 Hz supply, the synchronous speed will be directly proportional to 50 Hz. If it is a 60 Hz supply, synchronous speed will be directly proportional to that 60 Hz. Okay, so ns depends upon the supply frequency as well as number of poles. Now rotor is stationary, so the motor speed is n equal to 0. Okay, in induction motor the synchronous speed is different, rotor speed is different. Never rotor speed will be equal to synchronous speed. So the rotor speed is called the motor speed. Synchronous speed is decided by the manufacturer itself. So when the machine is stationary or when the machine is not rotating, the rotor speed or the motor speed n is equal to 0. Now the rotor is stationary while the stator flux is rotating, which will cut this stationary rotor conductors. So EMF will be induced in the rotor winding. If you see the frequency of this induced EMF, it will be equal to supply frequency. And if you see the magnitude of the EMF, it depends upon the relative velocity between the stator flux and the rotor conductors. And the direction of the EMF is given by Fleming's right hand rule. The induced EMF in the rotor will cause a current to flow in the rotor conductors because the rotor are shorted at the end. So this rotor current will oppose the cause producing it according to Lenz's law. So the cause producing the rotor current is the relative velocity between this stator field and the rotor conductors. So it will try to rotate in the same direction as the stator field. We can also say that these current carrying conductors, they are placed in the magnetic field, so they will experience a force and they start to rotate in the same direction as the stator. So the rotor now rotates in the same direction as the stator field, but this stator field's speed is synchronous speed ns. Rotor runs at a different speed n. So always there will be this relative velocity so that the motor will produce the torque. Synchronous speed is the speed of the rotating magnetic field. It is given by 120 F by P, where F is the supply frequency and P is the number of poles. The term slip is most important in induction motor. You see this picture where a car is moving and a dog is chasing the car. Let us assume that this car is the stator which is running at a speed of ns. Ns is synchronous speed. So this car is running at a constant speed of ns, and this dog speed, it depends on the requirement. So it is running at a speed of n. This speed, dog speed, is called the rotor speed or motor speed. So this dog can never catch up this synchronous speed. It can never catch up the speed of the car. So always there will be this difference will be there, but this difference may vary, but this dog can never touch the car. Okay. Only when there is this difference, the induction motor can develop the torque. So slip speed is given by ns minus n. So there should be some difference between ns and n. So the rotor will always run at a speed less than the synchronous speed. Always slip is represented in percentage most of the times. So slip is given by ns minus n divided by ns into 100. So the actual speed of the motor n, we can write it as ns into 1 minus s, where s value varies between 0 and 1. Suppose the motor is at rest, that is at standstill position, n is equal to 0. So if n is 0, slip will be equal to ns divided by ns, so it equal to 1. At no load or when it is rotating, slip value will be 0 or some small value will be there. Now we will see what do you mean by that slip frequency. So we saw that when the motor is stationary, the frequency of the rotor current is equal to supply frequency. But when the motor starts moving or rotating, everything will change. It depends upon the value of slip. So when the motor starts rotating, the frequency of the rotor current depends upon the slip speed, that is ns minus n. So slip speed is ns minus n, that will be equal to 120 f dash by p. So we have seen that supply frequency is f, and here the slip speed frequency is f dash, or the rotor frequency when the motor rotates, it will become f dash. We know synchronous speed is ns equal to 120 f by p. So let us find the slip. ns minus n divided by ns. So ns minus n, I am writing this 120 f dash by f p divided by this one. So it will give you f dash by f, or I can write it as f dash, that is the rotor frequency when the machine is running is equal to s times the supply frequency, or the rotor frequency depends upon the slip and frequency, supply frequency under running condition. So this frequency is called slip frequency. Let us see the different power stages in induction motor. So P in is the input, motor input, we give it to the stator. Out of the total input power, some will be lost and some will be reaching the rotor through the air gap. So it is represented as PG or PAG. Okay, so this G represents the air gap power and some will be lost as stator iron and copper loss. So this, out of this rotor input PG, some will be lost as copper loss, rotor copper loss. Rotor iron loss will be very small, so it is normally neglected, and the remaining power will reach the will be used as a mechanical power. So here S times PG is lost. So what will be remaining here? 1 minus S into PG will be converted into mechanical power. So this again, to reach the shaft, some will be lost as windage and friction loss, and only a part of it will be reaching the output. So efficiency is equal to P out divided by P in. In this you have to remember three important things. The rotor input power is PG, SPG is going as waste, and remaining 1 minus S times PG is available as mechanical power. Let us see the advantages. Because they have a simple and rugged construction, low maintenance, low cost, they can operate at much higher speed, it can produce sufficient torque, sufficiently high efficiency. So these are some of the advantages of induction motor. So when compared to DC motor cannot operate in explosive environment because of commutators. Here that commutator problem is not there, so they can operate in dusty and explosive environment. The efficiency of the motor varies with the speed, and they have low starting torque, especially squirrel cage motors, and speed decreases with increase in load. They have a wide range of applications starting from lifts, conveyors, food and chemical industries, paper sugar industry, chemical textile industry. So the points to remember here are, there are two types of three-phase induction motor: squirrel cage motor, which is widely used, and slip ring induction motor is preferred when you need high starting torque. And synchronous speed, we have Ns is equal to 120 F by P. F is the supply frequency and P is the number of poles. And slip is given by Ns minus N divided by Ns. And rotor input, if it is PG, SPG is the loss, and mechanical power will be equal to 1 minus S times PG. If you like the video, do subscribe to Read Electric Vehicle channel. Thank you.